going to, in the next couple of lectures, we are going to talk about language models. Broadly defined, these are models that work with language, with text. And obviously, these models are super important. You can use them for processing huge amount of text. You can use them for translation. You can use them for question answering. You can use them for many other applications. So at the heart of it is how we can input or sentences or words into these mathematical models, because inherently, obviously, sentences are composed of words or tokens, but mathematical models take real vectors as their input. So here you see a contradiction. In the previous lectures that we were talking about images, image models, we didn't have this problem because images, you can think about them as vectors, as real vectors, vectors with real numbers, discrete or whatever format that you have, and that format is compatible with the input of those models. But in language, we have this problem. Words are not mathematical objects that I can easily input to my mathematical model. Okay. So in order to deal with this problem, in 2014, there was a very influential paper called Word-to-Vec. I'm sure all of you are familiar with Word-to-Vec, but I'm giving a little bit of a historical context before moving to even more complex language models like ChatGPT and so on and so forth. Let's see where we started, what were the issues, how we are dealing with those issues. So in Word-to-Vec, it is clear from the name. So it is a module that takes words or tokens and it produces vectors or embeddings. So you might think, okay, so why do we need to train such a model? Maybe I can just represent my words with some random vectors, but unique. Let's say whenever I have, let's say Apple is great. Say I have a sentence like this. I'm going to map my vector Apple with some numbers. To some numbers is another token. I'm going to map it to some numbers. Great. It's another token. I'm going to map to some random numbers and I'll be done. So why do I need to learn a mapping of words to real vectors? Semantics, but something simpler than that. What properties would you like to see in these vectors? It's vague, right? So context, what does that mean? Right? So give me like more concrete similarities, right? So the first property I would like to see is that if two words are similar, their embeddings hopefully should also be quite similar. Right? That will make my mathematical the job of my mathematical modeling easier. Because now, so let's say I have two words, great and awesome, right? So they're more or less, similar. So it would be easier for my mathematical models to deal with roughly speaking, similar vectors. And so that's the first property that we want. I want similar words to be mapped to similar vectors or embeddings. Okay, is that enough? If I have similar words, it is mapped to similar vectors. So that is necessary, but perhaps I want something a little bit related to the, as you mentioned, context. So I want to have some sort of relationship encoded in my embeddings. Capture word relationship. Just as an example, suppose I have a vector representing apple, and I have a vector representing purple. If I sum these two up, apple plus purple, because now I'm representing them with vectors, right? So I can sum up the words. So I expect, okay, maybe the resulting vector should be close enough to a word like plum. It's like apple that is purple, right? So it has like some level of relationship embedded in my embedding space. So that's another property that would be great to have. Okay. All right, so how Word2Vec learns such embeddings? The idea is quite simple. I'm not going into like the details of it because it is not a classic method, but the main idea, we actually use it even in modern language models. The idea is to learn embeddings by predicting each word in our corpus by adjacent words. Each word in corpus by adjacent words. Okay, so let me explain that with an example. Again, consider the example, apple is great. Let's say we start with some random initializations for every token, every word in my vocabulary. So I get a vector for apple. I get a vector for the word is. And let's say I want to predict what would be the embedding for for my token grade. So the idea is simple. Let's sum these two up. I define a vector, let's say the apple, plus the embedding for the word is. You can normalize it. And effectively speaking, you just push it through a softmax. You have this word, and then you try to match it with one of the tokens, one of the embeddings that you have, to predict the next word, which is great. And then you can use back propagation to update your embeddings. So in other words, you can think about Word2Vec as a very simple neural network that basically just adds the embeddings of adjacent words. So you have now a vector, and then you try to align it in a way that is predicting the next word or the word that you have in mind correctly using subgroups. If it's differentiable, you just update your embeddings. Okay. And there are many variants of this method. But for example, you can think about, okay, so what is the window? What is the span window that I want to consider in order to my prediction. Maybe if I have a sentence, I don't care if I'm using the future words or the past words. I'm going to consider some words before the word that I'm targeting, and some words that like in front of the words that I'm targeting, and I'm going to use them as the input in order to predict the current word. That's fine. So that's one way. You can do it in a causal fashion, saying that, okay, I'm going to predict only the next word based on my inputs. But the good thing about this is that you don't need any labeling. So you start with some random initializations for your embeddings. You can take a big corpus like Wikipedia, and you can just iteratively train your embeddings until you converge to some stable embeddings. And hopefully those stable embeddings that you can capture will satisfy the two properties that we want. Similar words, hopefully, will be mapped to similar vectors. And it makes sense because if you have large enough corpus, let's say if you have two similar words, probably they have been used interchangeably in a different context. So the first property makes sense to hold. Similarly, the next property, because anyways, you are looking at the addition of your embeddings in order to predict the next token. So there are some level of relationship embedded in the vectors that we compute. Okay, so that's basically the main idea of word2vec, extremely influential paper, right? Because now we can input documents into our mathematical models by just replacing each word with a vector. But before we couldn't do it. And these vectors, they make sense because of having these properties. So let me pause, see if there are questions. All right. So if word2vec is great, and it is great, so what are we doing? Right? So why do I need to have other language models or other ways to encode information in my text? So I have vectors per word. I can just replace my words and tokens with these vectors, be done with it. So what is an issue with respect to word2vec that I need to deal with? Yes? Yeah, that is true, but I'm looking for something even simpler than that. Right. So maybe I can give an example along the answer that your friend mentioned. Let's consider two sentences. Apple is great, and my cell phone is broken. Great. Okay. So let's look at the word great. So in the first sentence, it is quite positive, right? So apple is great, and by apple I mean the fruit, maybe like the company, who knows, being baked. In the second one, my cell phone is broken. Great, it is negative. So this one has some positivity in it. This is negative. But in word2vec, we are encoding both of these tokens just using like one vector. There is no information with respect to that context. But this is like an extreme case. So in the extreme case, you can have one word with different meanings, even like sometimes positive, sometimes negative. But even in other cases, the context around a word can change and should change the embedding and the encoded information of that particular word, right? Because if we want to process sentences, paragraphs, passages, we need to somehow encode sentence-specific information, paragraph-specific information, passage-specific information. I cannot just replace every word in my paragraph with some fixed vectors and assume that, okay, now I have the information encoded in these vectors. And so I need to somehow represent, summarize the information in that paragraph, in that passage, into my embeddings. Right? So that is why we want word embeddings per context, per sentence, per paragraph. So we don't want them to be fixed. All right, so in 2017, there was a paper that I don't think it received as much as attention as other papers, but it started some new ways of thinking about this problem. The paper is, in fact, by OpenAI. At that time, I don't think they were big. It's called Unsupervised Sentiment Neuron. And the key finding that they had was that by just training the model in an unsupervised fashion, we can learn quite a lot about the language and about the concepts in our language. Unsupervised training. But just training the model in an quote unquote unsupervised fashion, we can learn a lot about the concepts and the language. Okay, even though the underlying idea was quite promising, basically unsupervised learning, they did okay in NLP benchmarks, not super great. It didn't really improve the state of the art at that point, and it performed moderately, not super great. But in 2018, there were a bunch of papers building on this idea that really took the state of the art to the next level, including models called GPTs, starting GPT 1 to 3 and ChatGPT 4 and ChatGPT, and other models such as BERT. So today I'm going to focus on BERT and another follow-up model called T5, if you have time. And next lecture, I'll focus on GPT models. We'll start with GPT 1 to 2 to 3 to 4 and ChatGPT, and we'll see how the evolution of these models have been and what really took them to the level that we see great quality in many instances, And obviously, they also have their issues that we'll cover in follow-up lectures. Okay. So next, I'm going to talk about BERT, which is a bidirectional encoder representation for transformers. Okay, so that's BERT. In order to understand BERT and also GPT models that we'll cover next lecture, I hope that you all have a clear idea about transformers, encoder and decoder architecture of transformers. We spend quite a bit of time to dig really deep into different blocks of transformers. So if you don't remember the details, definitely look at the notes for the transformer lecture. Really important, not only for today's lecture, but also for the next couple of lectures that we are going to have. But just to refresh your memory about transformers, let me just quickly draw the encoder-decoder architecture of a transformer. So refresh your memory. Encoder-decoder architecture of a transformer. Okay, so in the encoder side, we have some input words or tokens. First, we use a word-to-vec, the one that I explained. These are, again, fixed vectors. Doesn't really represent the context of that sentence, but that's a good initialization. That's what we are using. And we add positional embeddings to these word embeddings. That's the input to the encoder side. Right, so we had self-attention. Okay, so what is self-attention? You are looking at the values per token, and by using the attention coefficients, you are summing up the value vectors related to that token and having that as your output. Again, the output of your self-attention will be 3 vectors corresponding to the 3 inputs. Think about encoder. You start with 3 inputs. These representations evolve in your encoder, but the number of vectors remain the same. Okay, so you can have other operations like add and normalize. Okay, so here we add the inputs and normalize these vectors. Again, the output will be 3 vectors here. 1, 2, 3. And you apply an MLP or a fully connected network individually on each vector. Again, the output will be 3 vectors. So you're changing the dimensions if you wish, but you're not changing the number of vectors. It's a fully connected network. Again, you're going to have an additional add plus normalize. Okay, so the output will be 3 vectors. You can think about them as your word embeddings for this specific sentence. Right, so before your word embeddings, it was agnostic of that sentence. It was agnostic of that context. But now your output word embeddings, it is adjusted in a way to have the information of that sentence. Sentence-specific word embeddings. Maybe that is how you should think about your encoder. Paragraph-specific word embeddings, if you have your paragraph as input for your encoder. Make sense? In the decoder side, again, I'm doing it really quickly, just as a refresher. If you have some questions, definitely take a look at the lecture on the transformer. In fact, probably many of you know, we are posting the video lectures on YouTube, so you can even go back and watch. So in the decoder side, I want to, let's say, focus on seq-to-seq application, meaning that I'm generating another sequence for translation for other purposes. I'll start with the start of the sentence token. Again, a similar architecture to the encoder. Here I have self-attention, add and normalize. Here I'm going to have a fully connected network, add and normalize. But between these two, we have what? We have cross attention in order to bring the information from the encoder to the decoder side. So cross attention and we add and normalize on top of it. Okay, so let me just draw them. But let's say we have two inputs. Say I have x1, 2, just as an example. Okay, so you add and normalize. You add and normalize. Add and normalize. And you have two outputs. Okay, so just a review on what this cross attention is. For attention, we have three elements, right? Queries, keys, and values. So you look at this particular, some technical issues. Here it is. Add and normalize. Okay. So if you look at this particular token, so let's look at this one. Let's say it has a query vector Q1. So you look at like the embedding of it, you project it, you have like Q1. So you are looking at the similarity of Q1 with the keys corresponding to different elements in your encoder side. And based on that similarity, you are just summing up the values from the encoder side. Let's say these are mapped to keys and values like this. Q1 has similarity Q1 times K1 with value 1. It has the similarity of Q1 K2 with value 2, so on and so forth. And you replace that as your output vector. That's the cross attention. That's how you're bringing in information from your encoder side to your decoder. And you keep going. So again, the same number of vectors that you have as your input. So in many cases, you look at the last token here, the embedding of this last token. You push it through your softmax, where the output is the same size as the number of your vocabulary. And you see which token has the highest probability, and you predict that one. Okay. That's a quick review of the standard encoder decoder architecture for transformers. Just as a side note, here you don't have to predict the token with the highest probability. And in fact, that's not, in fact, a good practice. So the way that in practice it works, you can maybe consider the top 3 tokens and randomly take a sample, or you can consider the number of tokens that cover a certain probability in the probability space. So that will give you an adjustable number of tokens and take samples from that set. So that usually gives you like some variations in your output. So if you use any of these modern language models, maybe I'm skipping a little bit ahead of myself. When you don't like a response, you can push like a regenerate, right? Basically, the output is a probabilistic sampling based on these probabilities as a side note. So you don't have to take samples based on the maximum probability. Okay. So one note here that we talked in the transformer lecture, but I want to highlight. So the self-attention part in the encoder, every token can attend to any token. So if you look at the attention matrix here, attention matrix, which is the P matrix, if you remember, these are the probabilities of the similarities between keys and queries. It's a full matrix. Like it is not, it doesn't have a particular structure, but it is full. So it has numbers for every entry. But here, in the decoder side, we are masking the upper diagonal of the attention to ensure that tokens don't attend to the future tokens don't attend to the past tokens. So there's a causal structure that we are imposing ourselves on the attention matrix. So if you look at the attention here, this P, it will have numbers here, but the upper diagonal numbers, they're all zeros. Because we don't want the future tokens to influence the past tokens because they haven't been generated in that iteration. So here's the causal part of it. And I'm mentioning that because you're going to see that that come into play in some of these arguments. Okay. So that is a quick recap of encoder and decoder architecture of transformers. Right. So the main idea of BERT, and in fact other language models that are quite successful, is based on transfer learning. What is transfer learning? It is very expensive to collect annotated samples. For example, for question answering tasks. So it is quite difficult to collect good questions and good answers. Maybe you can collect it, I don't know, like 10,000, 100,000 of such cases, but it is not as easily scalable. So the idea is to first train these models in an unsupervised fashion, basically on the internet. Internet has like so much text in it. All the books, all the web pages, so on and so forth. So the model has then a good understanding of the language because it has seen different sentences, it has seen different contexts, so on and so forth. Then go back and fine-tune your model on your specific task with the weights that are starting with the pre-trained weights. That's the main idea of transfer learning. So let me just try this up. So main idea. It's quite natural, but it really made a big difference in the quality of these models. Transfer learning. So it is done in 2 steps. Step 1 is unsupervised. Pre-training. And step 2 is fine-tuning on a specific tasks. So with unsupervised pre-training, hopefully the model learns information, context of language modeling. Right. So that's the main idea. So what we are going to cover today, what we are going to cover next lecture, what state of the art language models that sometimes people claim they're taking us towards artificial general intelligence, or however you call it, is based on this idea, transfer learning. So you just train your model on a huge data set in an unsupervised fashion, and perhaps do quote unquote a level of fine tuning that I will describe in each case what we mean by it. Okay. Let me pause, see if there are any questions before I dive into details of these two steps for BERT. Yes.
Earlier discussed encoder decoder setup. So
yes.
In the cross attention layer, because the encoder doesn't have a cause of mind, that doesn't indirectly the decoder also has information about the future context?
No, because for example, for the translation task, in many cases, the ordering of like the words and tokens from one language to another language can be quite different. So in a way, it is very difficult to impose like, what should be the causation from the encoder to the decoder. Okay. Other questions? Yes?
You say you learn the language model.
Oh, very good question. Maybe I shouldn't say language model. It's a bad terminology. Maybe I should say context of language. How about that? Are you happier? Okay. So language modeling, it is used in different contexts by different definitions. Right? Sometimes if you're just using the next word prediction, like a decoder side, people call it a language model. But what about the encoder side? Is it a language model or not? So it is a little bit vague how people they use it. Maybe in this instance, we don't even need to use such a terminology. All right, so let's dive into the two steps of unsupervised pre-training and fine-tuning for BERT. So BERT, which is short for, okay, so I have the bidirectional encoder for transformers. It uses the encoder part of transformers. So that's in the name. So the way that it works, it uses the encoder side of transformers. Okay, so here's your encoder. You have tokens as your input. In the output of the encoder, you have the same number of tokens. The vectors are massaged in a way that you have sentence-specific representation for each token. That's the idea. And you can stack it up. You can, instead of like having one encoder, you can, again, have these as the input to another encoder and stack it up. Here it is. That is the model architecture of BERT. Easy, right? Because we already talked about encoder. Okay. So just the teaser, GPT models that we'll cover next lecture. So what is your guess? Are they using the encoder or the decoder side? They use the decoder side. That's the key difference between the model of BERT and the GPT models that we'll cover. But you can see how really amazing the design of a transformer is, right? Half of it can be used to train a model like BERT as encoder. Half of it can be used to train models like GPTs and ChatGPT that we have. It's amazing. Like one model architecture that can be used for different modeling purposes. Anyways, all right. So how are we going to? Okay, the way that BERT is trained, I'm going to explain their paper, but later on I'll talk about some follow-up works showing that what are the really essential parts of the paper, what are the essential parts of the training, because some parts of it are not like super important. So for the pre-training, unsupervised pre-training, they use two strategies. One is called masked language model, MLM, and the other one is called next sentence prediction. So in fact, both of these objectives are used simultaneously in pre-training BERT. But later on, people realized only this part is really essential. This part is not really bringing so much information to the model. But anyways, I'm going to explain it because I want to be complete with respect to how BERT is doing pre-training. Okay. So let's look at a BERT model. I'm going to take two sentences and have these two sentences as my input. Let's call them sentence A and sentence B. Sentence A and sentence B. Okay, so they add a separator token between these two sentences just to make sure that we know what they mean. And they add a CLS token to the beginning. And you have seen the CLS token before, right? We use that in Vision Transformer, the embedding of it as our classification. The origin of that is coming from the BERT paper. So they introduced the CLS token at the beginning of the first sentence. Okay, so each sentence obviously has different tokens. Say each has 3 tokens. So we have also a token for separator. We have a token for CLS. BERT is an encoder. So what does it mean? How many vectors I'm going to have in my output? The same number of vectors that I have in my input, but encoder. So every vector just gets transmitted through the encoder, but maybe the numbers change quite a bit or maybe slightly. Okay. So here I'm going to have one embedding for the CLS, 3 embeddings for this one embedding for this one, 1, 2, and 3 embeddings for this one. Okay. Okay. I need to train this in an unsupervised fashion, meaning that I don't want to have any labels. Okay. So for one part of the objective, they take 2 sentences from a corpus, let's say Wikipedia, but there are 2 cases. One is that these 2 sentences, sentence A comes before sentence B. These are 2 adjacent sentences. Or sentence B comes before sentence A. However, they label it as A or B. So this is encoded, this information is encoded in the embedding of the CLS token, or they want this information to be encoded as the embedding of the CLS token. So this is called the next sentence predictor, NSP, next sentence predictor. So they use this in a binary classification loss and predict 0 or 1, whether or not sentence A is coming before sentence B or vice versa. Quite easy because I'm taking samples and I can just randomly order them and have my ground truth label as 0 or 1, and I try to predict it based on this token embedding. I see some confused faces. Do you have a question? Is it clear? Take two sentences. Let's say sentence A actually comes before sentence B in my corpus, and my label is 1, right? So I want to predict the ground truth label of 1. But if it was the other way around, then I want to predict ground truth label of 0. Yes. Okay. Did I answer you?
No, I think I just need you to explain.
Yeah, sounds good. All right. So that's basically one part of my objective. And as I mentioned, in fact, this is not really important. But it was important because it introduces dummy token, CLS, that is used in many other contexts and applications. For example, in Bayesian transformers, we use like a CLS token, use that as the input to the classifier. Right? So the idea is interesting, but the contribution of it into the learning of BERT is not critical, I have to say. Okay. All right. So the critical part is the following. So they drop some of these input tokens, I believe 15% of them random. So you drop it, and instead you use like a mask token. And these masks, let's say X or Y or any mask, a mask token. Okay, and they are obviously being mapped to some vectors. And they try to recover the actual token using the embedded version of these mask tokens. So you push this into like a softmax and try to predict the ground truth token, but I know the ground truth token because I masked it myself. Okay, so that's the main idea of mask language modeling. As you can see, quite scalable, right? Because I don't need any labeling. It is just by randomly masking your inputs, 15%. In fact, any number between 10 to 20% is good enough. And try to recover the underlying mask token using the embedding associated with that. So what does it mean? It means that this vector has the information of the underlying mask token because of the context. That's how we are able to predict and unmask it. So in other words, this particular vector is a good representation of the word in that sentence, in that context, which is exactly what we were looking for. Really critical part in training the BERT in the first phase, in an unsupervised. Okay. So let me pause and see if there are questions before I move to the fine-tuning part. Now we learned a good language model that can take a sentence and it can provide the embeddings for each token specific to that sentence and specific to that context. Now we will use it in order to solve some particular downstream tasks by fine-tuning it. Any questions? Yes.
Are the initial embeddings initialized randomly or?
So there are different cases. You can use a mask just as a mask token, or you can use some placeholder tokens that doesn't mean anything, like X, Y, Z, so on and so forth, depending on like the number of mask tokens that you have. And more or less, they all work similar. Any other questions? Yes.
Where the initial embeddings for the words that are included into the model coming from in the first place? Are they coming from another model, or is it like they were just randomly generating embeddings for the words in the senses in the first place and then giving it to the model to respond to?
Yeah, as I mentioned, you can, it really doesn't make a big difference. You can have like some fixed tokens as your input, or you can even like have them learnable in your training. It really doesn't make a big difference, because at the end of the day you're looking at the output and you're trying to predict the input contribution is minimal in your output vector, because that's like a dummy token. So the important thing is to encode the information of the rest of the tokens in order to be able to predict the unmasked version of that token that you have. All right, so let's look at the next step, which is the fine-tuning step. Step 2, fine-tuning. Okay, so fine-tuning is task-specific. Right? So when BERT was introduced, we didn't have language models that can do many tasks at the same time. Right? So that's why we are at the time at the year 2018 when we are talking about this paper. Right? So we are going to take this model and fine-tune it on each particular task. Okay, so for classification problem, let's say sentiment analysis, it is quite easy because BERT has this CLS token whose embeddings, like the one that we had in Vision Transformer, can be used in a classifier. You can just train a projection head to classifier to predict your label for your classification problem. Obviously, you're still fine-tuning the whole network, but the weights change slightly, right? So you are not having your weights frozen. That won't work well. The projection head here is learned, but the number of parameters is quite small, and the rest of the parameters are changed quite slightly. So the learning can be done quite efficiently. So the other task that is usually considered as a benchmark is question answering. And there's a data set called SQUAD. I think stands for Stanford Question Answering Data Set. Maybe that's the abbreviation. And they have various versions in order to evaluate the quality of models for question answering. The way that it works, they have some questions and they have a passage. And the goal is to find the answer within that passage. So if you are now used to like models that you can just ask questions and get your answer, in 2018 this was a big deal, right? So not only, okay, so you give questions, but you give a little bit of a helper, right? So let's say you're asking a question about Lionel Messi, and you're giving the Wikipedia article about Lionel Messi as your passage, and then you want to get your answer. So that's the setup. In fact, if you we'll talk later on, but even modern language models, they use a little bit of a notion that we have here using retrieval augmented generation, but we'll talk about that later on. But here's basically the setup that you have. Okay, so maybe an example. When did Lionel Messi win the World Cup? And there's a passage, let's say, Wikipedia passage about Messi, and then, okay, so the answer is what? 2022, right? 22. All right, so here's the basic idea. And in fact, the way that it works is we want to, let's say, have the answer, let's say 2022, Lionel Messi won the World Cup in 2022. We want to have the position of the start and the end of the answer in this passage. And so that's the way that it works for this particular benchmark. Saying that, okay, so the starting token is this one, the last token, the end token for the answer is this one in this passage. Okay, so that's the data set. Okay, so how BERT can be used for that one? So I have my BERT model. I'm going to have the question as the input, and I'm going to have the passage as the second input. Obviously, there's a separator between the two. There's a CLS token at the beginning. Okay, BERT translates every token to a vector, right, in my output. So I'm going to have several outputs here with respect to my question, and I'm going to have several vectors of outputs for every word in my passage. Then I'm going to pick two vectors, fixed vectors, or you can have them learnable, as vectors of start of the response and a vector for the end of the response. And look at the inner product of your start vector with any of these tokens, and let's see where it picks. So you get a probability distribution. The highest position represents the start of the answer. Okay, so you get a probability distribution and say, okay, so here it is picked. Maybe my response starts from this particular token. And similarly for the end, let's say I have a peak of like this, and let's say this is the token that maximizes that inner product. And you can say, okay, so my response, the span of it is here in my passage. Okay, and when BERT was introduced, it actually really worked well on this particular task. It established, if I remember, state-of-the-art for question answering. And in 2018, it was a big deal to be able to solve this problem. Okay. Again, here we are fine-tuning it, right? So this is my objective. I'm fine-tuning, meaning that I'm changing my weights again for in my model, but slightly in order to learn. And perhaps I will learn two vectors, one for the start and one for the end. These are new parameters that I'm learning in my fine-tuning task, but not a huge number of parameters. Okay, various BERT models have been introduced. Just to give you an idea, the base model for BERT has about 110 million parameters. It has 12 blocks of encoders on top of each other. The large BERT, it has 340 million parameters. So as I mentioned, next I'm going to cover T5. That stands for text-to-text transfer transformer. I'm sure they try to have like different T's at the beginning of their words, but it's a nice and catchy name, T5. And the main idea of the paper, T5 paper, is to be able to compare different models that are trained based on transfer learning. Because especially after BERT, there have been like an explosion of such models. They take an architecture, they take a data set, they use a certain objective for pre-training, and they use that model in particular applications. And each paper, obviously, they claim they're state of the art in downstream tasks. But where the gains are coming from? Is it maybe because they had some fancier model, bigger model, or whether or not it is because of like their data set that they trained, or maybe the objective for their unsupervised learning, it was more critical than the other parts of it. So it wasn't very clear what are the important factors in order to have a successful transfer learning based on transformer architectures. And this paper from Google, since they had huge resources in terms of the compute, they tried to have a more systematic study of different aspects of this whole transfer learning to see what are the important elements in this pipeline so that we can look at the best practices and perhaps scale it up in order to achieve better performance. So that is the whole idea. So as I mentioned, comparing unsupervised pre-training methods, pre-trained methods is quite challenging. The factors that are involved is the data set that you're using for pre-training, is the model architecture and the size of the model that you're using, even some of perhaps smaller details. What is the optimizer that you're using? What are the hyperparameters that you have? So there are many factors, and different papers, they change a few of these in claiming some results for some downstream tasks. So it wasn't very clear at that point what are the important factors in having a successful transfer learning. All right, so this paper T5, they modeled every NLP problem as a text-to-text task. Modeled every NLP problem as a text-to-text task. So this is quite natural for some of the NLP problems like machine translation. Machine translation You, in fact, have a text-to-text task. You have an input text, you have an output text. But for some other problems, let's say classification, sentiment classification, or other types of problems, even regression problem, you don't have text as the output. But they modeled the output still as a string of text for classification, for regression, for other types of problems. For example, in the classification, to the input, they add a task prefix saying that, okay, if you're classifying your inputs as acceptable or not acceptable, you can add that as your prefix, saying that if it is acceptable or not acceptable as your task prefix, and have your model to output yes or no for this particular label. Even for the regression problem, you can model your output, which is a number, as a string. Let's say if your regression value is 3.5, you can model it as a string. And for each task, they add as I mentioned, a task prefix to the input. So the model, the idea here is to have a more universal model. It is not particularly specific for translation or for regression analysis, for classification analysis. So here what you have is some task prefix plus your input prompt. Here you have T5, and here you have output as a text. So that's the modeling that they have. Okay, so now that you have probably seen models like ChatGPT and stuff, you may say, oh, well, what are they doing, right? So why do you add like a task prefix? Why can't I just like ask questions directly from my model, and my model figure out what is the task and respond? Like, we are talking about pre-ChatGPT era. So in that year, still it was a good formulation to have a little bit of universality. So the catch here, so they pre-train their model T5 in an unsupervised manner, but still, in many of the experiments, they fine-tune it specifically for downstream tasks, meaning that in majority of their experiments, they still have a specific model for specific tasks. So you may think that, okay, so why then they need to add a task prefix? Because they're anyways going to take this in the pre-trained model and fine-tune it on a particular task, for example, for translation, for classification, question and answering. So why do we need to add a task prefix? Because in some of their experiments, they use the model in a more universal way when they are doing fine-tuning for maybe multiple tasks. So that's basically the setup that they have considered. But in majority of the experiment, really it is not necessary to have this task prefix, because anyways, in their fine-tuned model, the model is fine-tuned on particular task, and that's how they're going to evaluate. But it's a nice feature, because now you can have experimentation saying that, oh, but what if like I use several tasks as my fine-tuning objective, and now I can differentiate in my input using the task prefix how my model should behave with respect to those types of things. Right. Subtle point, but I just wanted to highlight that. Okay, so for their model architectures, so they have considered three types of models. One is standard transformers. Basically encoder-decoder architecture that we have discussed. Encoder, and here you have a decoder. I hope that now you are pretty comfortable with this architecture. And then you generate your output. They also considered something that they call language model, but I would just call it the decoder, transformer decoder. So the idea here is to use the decoder side. And the main difference here is that if you look at the attention, if you remember in the decoder side, in the attention, we were using the masked version. So the attention numbers above the diagonal is 0. But here in the encoder side, if you are looking at the cross attention, the attention can be a full matrix. And they considered another model between these two. They call it the prefix language model, which is a combination of 1 plus 2. Not really important, so I won't go into the details. Basically, the prefix language model, they consider is that, okay, maybe like for a couple of first tokens, your attention map is full, and for the rest, then you have this causal attention, that you have that zeroing out of some of the upper diagonal elements. Okay, so that's about their model architectures. What about like the objectives? So mainly they considered the original objective in the BERT paper, which is based on input masking. And they have considered a couple of variations of input masking. One variation is called span masking. Which is the following. Suppose you have the following as your original text. Let's say, thank you for inviting me to your party. Okay, now I want to create a masked version of this. To be used as the input to my model. So I can recover the masks as mask tokens in my output. So the mask version can be something like this. Thank you. And then you have a mask token, for example, this token that they considered, me to, so on and so forth. Here, as you can see, for inviting, 2 tokens are masked by just one mask token, which is like, you know, a dummy token X. That's called span masking. in the literature, people, they have done like different variations of it. For example, you can just mask individual tokens. You can mask a chunk of text. So this is the objective that they have considered among many other objectives. And here the output, because as your output, you want to have a text. It's a text-to-text model. You want to predict something like this: the mask, and then the tokens corresponding to that mask. Inviting. So this is called span masking, very similar to the first unsupervised objective that we talked in the BERT paper. Okay. And there, after pre-training, after unsupervised training, they still fine-tune it on specific tasks. For example, for glue benchmark, it's a classification task. For summarization, for squad, which is a question answering, and other tasks, they take the model and they fine-tune on it. It's not a universal model. All right, so I'm not obviously going to go into the details of all of their experiments, but I want to highlight some of their findings, some of the high-level messages that I think is useful just to keep in mind. I think one finding that they had, and it is verified in many other papers, pre-training actually helps in all of these tasks. So this whole transfer learning pipeline, when you are doing pre-training, unsupervised training, and then you're fine-tuning on a specific task, in fact, it is better than just hyper-focusing on one particular task. Pre-training helps in all tasks. And they have run a lot of experiments to show this. So I'm just highlighting their top line messages. Okay. So one message that I'm not sure, in fact, if it is valid in a broader sense. They argue that bidirectional attention maps, having bidirectional attention maps like BERT, is actually helpful compared to the attentions that are causal, meaning that the upper diagonal is 0. In fact, we'll talk in the GPT models that might not be true. So depending on the setup, in their experiments here, it was true that having bidirectional maps like BERT is helpful. But what if you consider other setups, like bigger model, bigger data sets? What happens in those cases? Okay, so that's why I'm going to put a question mark here in terms of the second findings that they have. Bidirectional attention helps. Maybe. Okay, but anyway, so that's the second findings that they have. In terms of the pre-training objective, they found that the BERT style objective is actually the best. I mean, you're just masking, especially the span version of it, masking part of the input and asking your model to recover it. Among different objectives that they have tried, that worked the best. The pre-training objective, the span masking, work the best. Other objectives maybe work relatively similarly to this objective or worse than this objective. And in span masking, one hyperparameter is what is the probability that you are masking your inputs. They did a sensitivity analysis in the BERT paper. They are using 15% of the inputs to be masked. They found that any number between 10 to 25%, more or less the same. So it really doesn't matter if you're masking 10% of your input or 25% of your input. You more or less achieve comparable results. So 10 to 25% masking, all good. Not a very sensitive hyperparameter in training. Okay. What about the data set? For their training, they used a data set, the common crowd data set. Now, Common Crowd is a non-profit organization that basically snapshots the web at some particular time and it stores the content on the web. So they take, and every month I think they dump a huge amount of data, a few terabytes, and it is accessible. Everyone can go and download it. So they use this data set, but they cleaned it up. So because it is web, so not every text on the web, it is a natural language, right? So that you have a lot of code, like HTML code, other types of code. You have a lot of other types of input. So they use some easy pre-filtering. For example, when you have like some sort of annotations or not, you can filter out many of the non-natural language elements. For example, I don't know, if you have a curly bracket, how often we use a curly bracket in a natural language? You just get rid of all of those parts in your input. So they cleaned up after a lot of filtering. They cleaned up a data set called C4, which is a subset of the Common Crowd data set. And they pre-trained on the original data set without filtering, and also on the filtered version, which is much smaller. And what they found is that, in fact, the pre-trained model on the smaller but higher quality data set was better than pre-training a model on a bigger but low quality data set, which is quite intuitive, but that's something that verified. Okay. So they take all of these good practices. So these were some of the highlights of their experimentations. They did run like so many experiments. So it's a good paper. Their models and experiments are quite useful. I'm just covering a subset of the messages that they had, important parts of it. But and after all of these experimentations, they put everything together, put all together. Okay, they said encoder decoder architecture, meaning that when you have a full attention in your encoder side, in their experiment it worked the best, so they're going to use that encoder decoder architecture. As their objective, they use span prediction objective. For their data set, the cleaned up common crawl dataset. For their pre-training, they use a multitask pre-training, meaning that because they have like this task prefix, they can put all of the tasks and pre-train according to all of them. And the final message is that bigger models train bigger models trained longer. These are like the top top messages, the highlight of their experimentations, and it worked pretty well for them. So they took these and they scaled up their model. They ran the training of the model for longer, and that's what T5 models are. They have different versions of T5 encoders. T5 small has 60 million parameters. And I believe the larger model that they have has 11 billion parameters. T5 large, 11 billion parameters. These models, at the time it was introduced, it established state of the art at the time. For every task except translation. So T5 encoder performed pretty well for everything that they tested except translation. And the reason for translation, it didn't work well because in the data set, in the C4 data set, they only considered English as the language when they are doing filtering. So they filter out other languages. So their encoder basically only has seen English. So it performed quite poorly on translation, for example, from English to French and other languages. But T5 remains to be one of the best text encoders that you can use in many applications. In fact, we talked about diffusion models, right? Text to image diffusion models. And there we were using, a text encoder to represent text with some vectors. It has been shown recently, if you use T5 as your text encoder, you get higher quality images in your generation. So that's why I highlighted this set of models as pretty good encoders, and they have done a lot of experimentations just to make sure that the training, the model architectures are at least empirically justified. Okay. So that is all I had for this paper. Let me pause and see if there are questions before changing the gear and talking about another set of models. Yes.
So, during this time that did they ever consider doing pre-training over the data set multiple times, like doing several blocks?
So usually in fine-tuning, it is not good to repeat on different samples. In the pre-training, because your data set is like so big, there is no coming back to any sample. In fine-tuning, the best practice is to have large enough data set for the fine-tuning task that you don't come back and revisit those samples. It has been shown if you do that, model overfits. So if you come back and visit a sample more than once, a couple of times, there's a risk of overfitting to the data set that we are fine-tuning. All right. Any other questions? Yes.
You didn't draw a question mark at the site using about like 10 to 25% is equal to basket. And I just think it's still true.
So for the objective that they consider, that level of masking is good. Right? So you don't want to mask higher level. It will hurt. If you mask lower level, you may not learn something meaningful. But by no means this is the only objective that works. In fact, the next set of models that I'm going to talk about, they use a very different objective for their pre-training. Any other questions? So T5, right? So if people they say, "Oh, I'm using a T5 text encoder," then you have an idea of what is really going. All right. So next, I'm going to talk about another set of language models called GPT, short for Generative Pre-trained Transformers. Pre-trained transformers. Okay, just a quick recap of about the transformer architecture. I hope you are all now comfortable with the transformer architecture because we have covered it a few times already. So there is an encoder side. You have input tokens, x1, x2 to, let's say, xn. In the encoder, you have self-attention, then add and normalize, then fully connected network or MLP, another add and normalize. So the output of the transformer encoder is the same number of vectors that you have in your input. And we talked that the attention here, we don't have any constraint. That's why we are saying bidirectional attention. Every token can attend to every token. On the decoder side, let's say we have already generated some tokens, y1 to, let's say, yk. Again, there's a layer of self-attention, add and normalize. At the end, we have a fully connected network applied to each individual vector, add and normalize. And as you know, here in the middle, we have cross attention, add and normalize. Okay, so the output goes to softmax, and we predict the next token in an autoregressive fashion. And if we look at the attention map here, the upper diagonal is 0. So it has only lower diagonal numbers. If you're not comfortable with transformer, please, again, go back and look at the transformer lecture. Extremely important. I want you to be able to draw and understand transformers in 1 minute. Right? So it is very important to keep the architecture in mind. So BERT takes the encoder part, it stacks on top of each other. That is the model that they consider, and they use that model in a transfer learning setup, meaning that they first, in an unsupervised way, train that model and they fine-tune it on particular tasks. On the other hand, GPT models, they take the decoder side. They take the decoder side, they stack it on top of each other, and they do exactly the same thing. They use it in a transfer learning setup. They pre-train it and they fine-tune it for some particular underlying task. That is the key difference between GPT and BERT. Right, so again, we are going to use transfer learning. Which involves pre-training in an unsupervised fashion and then fine-tuning on specific tasks. Okay, so let's look at GPT-1, right? Because that's the original model, and we'll see what was the evolution of GPTs, how GPT-2 is different than GPT-1, how GPT-3 is different than GPT-2, and then how ChatGPT is different than all of these models. So for the pre-training task, GPT pre-training task, they just use the next token prediction. Because that is the task of the decoder. So you're predicting the next token. You can look at the text, entire text from the web. You have a lot of sentences. You can try to predict the next token given the context that your model has seen so far. Very easy, very clean objective. This helps the model to understand the language. Sometimes it is referred to as like self-supervised learning or unsupervised learning. Who cares? That's basically the way that it is being trained. Okay. And then you go and fine-tune it on underlying tasks. And fine-tuning is done with labels. You need labeled samples for your underlying tasks. For example, if you're doing sentiment analysis, if you want to have your model look at the paragraph and say if it is a positive or negative, or have like other types of outputs, it has to have labels. If you want to have question answering, you need to have several questions and answer pairs, and fine-tune your model in order to be specific for those tasks. Okay, so fine-tuning is good, but it has its own issues. So one of the main issues of fine-tuning is that even though we are making the job of model for the underlying task much easier by first pre-training in an unsupervised fashion, but still model needs to see a lot of examples in order to be successful in that particular downstream task. So in other words, you still need too many labeled samples. Just to give you an idea, roughly speaking, for each downstream task, you need 100K labeled samples, more or less. That is the order that you need to have in terms of your label samples in order to be able to successfully fine-tune your model. Maybe okay for some applications, but many applications, 100,000 labeled samples, it is not quite easy to obtain. And the second issue is in fact related to the first issue. You can overfit in the fine-tuning phase. So if you have limited number of samples, and you may say, okay, I'm going to have like several epochs in my fine-tuning, I'll revisit basically samples, huge risk of overfitting. And in fact, that is being shown. It is not a good practice to revisit a sample during the fine-tuning phase. And the third issue of this approach is that it is not helping the model in terms of context switch. It is not fluid in context switch. Now, sometimes you may have a natural text, but maybe in the middle you want to do like some sort of mathematical computation. For example, you are saying, okay, so the salary of this engineer based on the information that was given is 50K, 100K, right? So you're doing some level of mathematical computation. These models are not good in terms of mixing different contexts and different tasks. That's one of the main issues. All right, so in order to address these issues in GPT-1, GPT-2 was introduced, the second generation of GPTs. And the main idea is to use meta-learning instead of fine-tuning. Right, so GPT-2 uses exactly the same pre-training approach, next token prediction, but they don't fine-tune. They do zero-shot learning. Zero-shot learning, it's a fancy way of saying no fine-tuning. You just learn one model. That's it. I think this way of thinking was really critical to achieve some of the LLMs that we currently have. Because previously people, everyone, most people, they were thinking, okay, so you have a pre-trained model, it understands language, but probably it is not going to be good enough to be able to solve every possible task. Just one model. So therefore, we have to fine-tune to be able to have a good performance on individual tasks. And when you fine-tune, then you have many models. Depending on the number of tasks, you have the same number of models. Not universal, right? Not very easy to use them. So the idea is to just abandon that approach and think about just a single model that is capable of tackling all of the downstream tasks. That's called zero-shot learning without fine-tuning. So in inference time, we have no parameter change. Fantastic. And they use prompt in order to pass an instruction to the model to say, okay, what the output should look like for this particular input. Pass instruction to model using input prompt. This is very similar to the task prefix that was used in the T5, in fact. So just to give you an example, you can have a model GPT-2. The input has a prefix, let's say question, answer. This is the task prefix. And then you ask your question here, and you hope that your model is able to answer to that question. You have that task prefix. And GPT-2 had about 1.5 billion parameters. Okay, fantastic, right? So one model to deal with all of these underlying tasks. But it didn't work well. But it did not work well. The idea is good. It, basically gets a way of individual models fine-tuned for specific tasks, but compared to each of those models, it did okay, but it wasn't great. But in the paper, if you take a look, one of the findings is that they tried different models with different sizes. And even though they didn't outperform state-of-the-art in any of the benchmarks, one of the key observations was that scaling the model was helpful. All right. So that's GPT-2. We got rid of specific models for specific downstream tasks. We have a single model. The model is quite big, 1.5 billion parameters. But it was okay, but we have a good observation. Scaling of the model was helpful in all of these tasks. Okay. Then it comes GPT-3. Your OpenAI, you have a lot of GPUs. You want to improve your model, and you have this observation. What would you suggest? Make it bigger. Exactly. By how much? So you have 1.5 billion parameters in GPT-2. What would be, like, let's say you are the CEO of OpenAI, what would be the number of parameters that you would like to have in the next generation?
100 times bigger.
Fantastic, 100 times bigger. 100 times 1.5 billion will give me 150 billion, right? Roughly speaking, parameters. In fact, you are not off. GPT-3 has 175 billion parameters. It is more than 100 times bigger than the original GPT, the previous version of GPT-2. So that's one change compared to GPT-2. So the second change that they considered was to be perhaps a little bit less ambitious in terms of getting rid of the fine-tuning part. Because there are two extremes. One is that you have zero-shot learning, where you have one model whatsoever, you just use this model. And the other extreme is that you have fine-tune on specific tasks. So GPT-1 was here. GPT-2 was here. How about somewhere here for GPT-3? Maybe instead of zero-shot learning, I can do one-shot learning, or I can do 2-shot learning, or I can do 10-shot learning. These are examples from meta-learning, where you show your model a couple of examples and then ask your model to perform a particular task. That's called, K-shot learning. It's a well-studied problem in the meta-learning. So that's precisely what they do. Instead of 0-shot learning, they still have 0-shot learning. But they consider K-shot learning, meaning that they show K examples to the model in the fine-tuning phase. So the way it works, you have GPT-3, then you have a question here that you want to get an answer. And you provide a couple of examples, maybe 10 examples. If you're asking a particular question, you say, okay, so maybe here's another question, and it was the answer for this question. Here's another question, it was the answer for that question. These are like examples to show your model what you mean by asking a question, and how the model should get the output. Okay, so this is called the model context window, where you add these examples. But at the end of the day, you get one model. That's it. So one model for all of the tasks that you have. And this works pretty well on many benchmarks, like question answering, in sentiment analysis, so on and so forth. So what was the main changes? One is that they have 100 times bigger model compared to GPT-2, and they do a level of fine-tuning, but using K-shot learning, showing a couple of examples for a specific prompt, just helping models to understand the context a little bit better, to respond properly to some of the questions. So that was a GPT-3. Right, so next we are going to talk about training a model like ChatGPT. Okay, so what is this model? So you have a language model. It has some input, user prompt, and you want a good response to that particular prompt. So the training of a model like ChatGPT has been done in 3 steps. And I'll explain in a high level what these steps are. I would say 2 of these steps are pretty trivial and straightforward. But one step is more technical, and we are going to dive a little bit deeper into that part to understand, how that is being done. Okay. So in step 1, basically take a pre-trained GPT model and fine-tune on some demonstration data, like supervised learning that we have seen in the previous versions of GPT. Take a pre-trained GPT model and fine-tune on demonstration data. So this is called supervised fine tuning. SFT. Basically what it does, you gather some demonstration examples, you have some annotators, you have some prompts, and some responses written by those annotators. And you try to fine-tune your model to increase the probability of generating those responses written by the annotators, assuming the responses are high quality by those annotators. So in other words, these came from annotators, labelers, however you want to call it. Really straightforward, right? Nothing really fancy, but obviously it is very costly because you need a lot of examples in order to fine-tune a model like a GPT-3 or GPT-4 with hundreds of billions of parameters. And getting high-quality responses might not be quite easy because these annotators are people, right? And they might have some knowledge about some topics that they can provide some responses, but they might have some responses that are low quality with respect to like different types of prompts. So the quality of these responses also matter a lot. How to flag some low quality responses, so on and so forth. There's a lot of data processing going on here, but that's basically the first step. Okay, so the second step is to do the same thing, but make it easier for annotators. Because here, suppose you are an annotator, I'm giving you a prompt. I don't know, what is the distance of sun from Earth? So it is sometimes difficult, to have these facts. Or, if you are asking a question, I don't know, I have like 2 apples and whatever. You can, have some questions and ask annotators to provide the response to those questions. But it's very time consuming. Okay. So how can we get information from human annotators, but in a simpler manner? That's basically the second step. Step 2. Okay, so we generate several responses for a particular prompt using the model. And I'll explain how this can be done. And we ask annotators to rank them, to rank or score them. Okay. So in this case, you have, again, your model. It's called a ChatGPT or whatever model. It is basically a chatbot that you have. You have a prompt. You can, in fact, generate many outputs, many responses from this model. I'll explain different procedures to do that, but the output is not necessarily deterministic. It is a probabilistic output. You can have various types of generations. Let's say you have response 1, response 2 to response K, automatically generated by the model. And you ask the labeler annotator to either rank or score these responses. And this information is used to train a quote unquote a reward model. This reward model basically assigns the quality scores for different responses generated for different types of questions. Assigns quality scores for a given pair of prompt and response. Okay, so as you can see, again, we are getting information from human annotators in this step, but it is much, much, much cheaper and simpler, because in the extreme case where k is equal to 2, you are showing 2 responses to a human annotator for a given prompt and asking the user to say which one it prefers, 1 or 2. And that is as simple as that. So you are not asking the human annotator in order to write a full response for you. So this is scalable. It's more scalable than the first step. It is easier to collect. And that is partially why we have the second step. So you have different options in order to, at the end of the day, this reward model, it's another neural network that gets the pair of your prompt and the possible response to that prompt and assigns a quality score, let's say between 0 and 1. Right? So that's the reward model that you have. Assigns a number between 0 and 1. Okay. All right, so in order to train this reward model, you can start again with some pre-trained GPT and have some linear head that maps the output embedding to a number between 0 and 1. And you can use the samples collected in this step 2 in order to do that, learning process. However, if you ask annotators just to assign a numerical value in terms of the quality to a response, you lose calibration, because let's say person A is very tough in terms of grading. So I'm going to assign, like maybe 0 and 0.1, even like to the best response. I hear maybe it is not perfect, but maybe another person, is in a good mood, saying that okay, yeah, it's fine. Everyone gets an, right, basically. So you can get this calibration problem. So that's partially why it is better to rank, right? Because when you're ranking, when you're sorting, you're getting rid of that calibration problem. And after that, you can use different approaches to basically turn those ranks into real values between 0 and 1 without having calibration issues. Okay. So that's basically the reward model. You have the prompt, you have the response, and your reward model assigns a value between 0 and 1 to that particular response. And if you have heard about quote-unquote alignment, for example, if you want your model to not produce toxic responses, or like some responses that you don't want your model to generate, perhaps this is the model that you can basically encode such constraints, saying that basically if the response, I don't know, has some sort of biases or have some issues, assign a low value, low reward, and that basically takes us to step 3, where we are going to use this reward model to fine-tune the original language model. Okay, so that's step 3. Again, step 1 was having humans who have inputs and outputs, fine-tune your model, supervised fine-tuning. Step 2, we just train the reward model. That's it, right? So it is that there is no connection between step 1 and 2. Now in step 3, we put things together. We use the reward model to improve the quality of the original model. Original, or you can call it base model. Okay, so here's the base model, base LLM. You have your prompt. It generates a response. But now you can use the response that is generated plus this prompt as an input to your reward model. This will generate a score about the quality of the response. And if everything is differentiable, which is, these are neural networks, you can use the output of your reward model and backprop that in an algorithm that I'm going to talk about next to improve the base model. Basically, you use this information, the quality, and you backprop that in order to improve your base model. And that is done by viewing this problem as a deep reinforcement learning problem. Deep reinforcement learning, and you can use different algorithms in order to do that. We are going to discuss those algorithms in the next part of today's lecture. But that's basically, broadly speaking, this is how it is being trained. Okay. So first, you have a good base model. You gather a lot of inputs and outputs. You fine-tune your model. Good. But again, the bottleneck here is that gathering high-quality input and outputs, it's very expensive. That's why we are using this proxy, this reward modeling, because it is easier to gather this information using human annotators. So I have this reward model. So this provides a feedback for me about a particular response, about a particular prompt. But now I can use this in order to update my actual base model. So if your base model generates a response whose reward is not good, then I can penalize the generation of that response, meaning that I can adjust my weights so that the probability of that response to be generated becomes lower. And hopefully, after basically fine-tuning, I won't generate the responses with low quality. Obviously, this really depends on this reward model, because that tells you basically the quality of your output. So in many cases, if you just use a separate reward model as is, you'll collapse, meaning that you'll generate some gibberish outputs artificially having a high reward. And so that's basically what it is being observed in practice. So that is why I'll talk about the details of it. That's why you usually have a combination of rewards, meaning that you want to increase your reward, but you don't want to go too far off from your base model. So you want to have basically remain close to your original model, because the original model is trained, pre-trained, first of all, and also trained on a lot of examples. So the outputs are already high quality. So reward model is, making it perfect and also, quote unquote, aligning it to not produce, for example, toxic outputs or sensitive information, so on and so forth. But you don't want to really rely on your reward model for the full generation. So that's why usually in practice, a combination of reward functions are considered in step 3. I'll talk about the details and the way that different formulations have been considered. But that's basically the high level. You can take this, you can modify different steps, but that's one way to train these more general purpose language models like ChatGPT, many other models. Last time I checked, I think there was more than 165,000 different language models out there. So many of them are trained using some versions of this. And by no means that is it. It's just one way. And as you can see, there's a lot of engineering and human annotations going on. So you should, I'm basically just telling you what is being done. I'm not telling you this is the only way. And I'll, in the next lectures, I'll talk about several weaknesses of these models, some of them fundamental issues of these models. So today we are learning how it is being trained, and in the next lectures, we are going to see what are the issues, of these models. We'll think a little bit about some ways to more fundamentally think about this problem. But let me pause here, see if there are questions, and after that I'll move on to some technical discussions about deep RL, because that's going to be very important for understanding the way that is, the step 2 and 3 are being. Yes, go ahead.
Is the base LLM without the supervised fine-tuning?
No, it is with supervised fine-tuning. My mic died. It's big tech, guys. I'm being censored. These models are awesome, by the way. Okay. Let me see. We change the battery. The mic works. Yes, go ahead. Yep.
So instead to consider that the responses that we get from the model, so for example, we have 10 responses and all of them are of the same low quality or something like that, they're all going to be scored 0. And there's a reason for that. So for example, it's because we're generating something about hate speech or conspiracy theories or whatever, I don't know. So how is the reward model going to be knowing that they're assigning it a score that is low because of the fact that it was considering they were generating something that was about the conspiracy?
Yeah, fantastic question. That's always a trade-off between the two extremes of assigning scores to some generations. So in the one extreme, you have some numerical values. Let's say if all of your responses are low quality, you actually want to assign numbers close to 0 to all of them. Right? So none of them, they're close to 1. On the other hand, that creates the calibration issue, as I mentioned, right? So because different humans, they can have like different ways of scoring. On the other extreme, if you're doing ranking, absolutely, you lose that information. If you have 2 responses, both of them are bad, you're assigning basically 0 and 1 in the binary case. Sometimes elections work like that, as you might know. But that gets rid of the calibration problem. So it's a trade-off. But it seems the advantage of the ranking outweighs the disadvantage. And I'm sure different companies, they look into like different ways of having maybe soft scores, ranking scores, doing different types of calibrations. it's an active area of research. I'm not saying this is the only way, but I'm basically highlighting pros and cons. And I thank you for the question, because I actually forgot to tell you how we can generate several responses for a particular prompt. So let me just do that as a side note. So in your language model, so these are like input tokens that you have. And at the end, you decode in an autoregressive fashion, meaning that you're generating your next token, and then you add that next token to your input, and you keep going. Right? So that's the way that the generation works. The decoder of the transformer, it goes to the softmax. This embedding, it gives you a probability on your entire vocabulary, which is, let's say, roughly speaking, 50K. So here you have different choices in terms of your sampling. One choice is that always pick the token with the highest probability. That seems reasonable. Right? So you say, okay, I'm just gonna, this token has the highest probability. I'll generate this particular token, add that to your input, again, generate the next token based on this particular. In this case, you always generate one, because that's the rule that you have. But in practice, what people they do, and it seems empirically it works better, is to not consider only the top token, maybe consider the top K tokens. Suppose these are the K tokens that basically get the highest probability after the softmax. So you don't pick the highest. You consider the top K and maybe randomly select among them. Okay, so this is called top K sampling. Which basically considers, not surprisingly, top K tokens and randomly select one. Okay, so but here you're losing the probabilities, right? Because you use the probability to have the threshold top K, and then you uniformly sample. The other approach is called top P, where you consider samples with probabilities. The combined probabilities add up to P. So instead of having a fixed K, now you have a fixed probability to say, okay, so these are the tokens. There are some probabilities, up to P, and I'm going to take a token uniformly, randomly from that set. Samples, not samples, maybe tokens. Tokens where probabilities add up to P. Okay. So that's called top P. So if you hear people in doing language modeling, if they say, oh, I'm using top K generation, basically top K tokens, and they randomly set top P generation, that's basically how they do it. That means for a response, for an input, you can have multiple outputs. You can have different types of generations, and that helps in terms of exploring the output space compared to just having the highest token selected as the next. So these are the two ways of generating multiple responses for a prompt. And again, in step 2, you're asking your annotator in order to rank them and use that information to train a reward model. All right. Next, I'm going to spend some time about covering some basic concepts of deep reinforcement learning, because maybe that is the only non-trivial step in the whole training pipeline that I told you. Right? So the rest is, important human annotation, so on and so forth, but the technical, I think, element is how to use the reward model in order to make the original model better. And that is done via deep reinforcement learning. And the whole process is called reinforcement learning with human feedback. All right. So I don't assume that you guys are familiar with deep reinforcement learning. So I'm going to do a quick recap of the most important concepts, and you're going to see many of them are actually quite natural. So obviously, deep reinforcement learning, it's by itself is a course, but we are going to have a quick review and just touch base on like the most important concept, especially for training language models. Okay, so deep reinforcement learning recap. So deep reinforcement learning or reinforcement learning in general is used to model sequential decision making. To model sequential decision making process. You can basically model the entire world as a reinforcement learning. You can model your life as a reinforcement learning problem. So the way it works, there's a state. You're at a particular state at time t in your life, and you're the agent, and you take an action at that time. You took an action, you came to the class today. Maybe good, maybe not good. But that action, basically you decided to come to the class today at this time. And this action goes to the environment and it basically takes you to a new state in your life. Sometimes you made the decision to come to the class and, God forbid, you hit by a bus. There you go. That's a fatal state. Okay. Hopefully that won't happen to you, but there's randomness. All right. But you can model the different problems. For example, if you're playing chess, you have an action, then the state is basically the state of the board. Sometimes you have a stochasticity in the environment, sometimes you don't. Right? So whatever action you take, it takes you to maybe deterministically to the next state. And at each step, you collect the reward. Sometimes this reward may not be immediate. That's basically called sparse reward. Sometimes you want to go from point A to point B, and you are making a lot of decisions along the way. At the end, you will have like this huge reward. Sometimes you collect reward even along the process. So you can have different reward models. Okay. So what are the elements of this formulation? One is state, S, a set of states that determines the state that the agent is. A is a set of actions. R is the reward function. And P is the transition probability. Which basically models the environment. Meaning that if you are at a particular state, you take a particular action, which state you end up with. That's basically the transition probability. In many cases, it is unknown because you don't know how the environment is working. There are some approaches It's called like model-based RL, where you try to gather samples and model the environment. Quite difficult, right? Because environment in real life can be pretty stochastic, can be non-smooth. If you have like a robot exploring an area, maybe like 99.9% of like the area is like smooth and nice, and maybe there's a hole and that's non-smooth, and that those situations can be quite difficult to characterize. And the model free RL doesn't make any assumptions with respect to the environment and basically tries to use the samples in order to have a proper learn. So these are the elements for the problem setup. And what we want to basically learn is something called policy. Policy pi is a function that tells you what to do. You're at a state S, and it tells you what action you should take. So that's basically called policy, that provides us the best action or some action, depending on like what that policy is intended to do at particular states. Okay, now like we are talking about language models. Right now I suddenly jumped to RL, which you may have heard of RL in the context of robotics or in the context of games, but how can we interpret a language model using this formulation? Interpreting a language model as an RL agent. Okay, so here's my language model. I want to interpret that as a policy. A policy that tells me at what state, which action I should take. So what is the input to my language model? It is the original prompt or question that I have, and responses, the tokens that have been generated, let's say up to time t. Tokens generated. So this is my state. That's ST. That's where I am at time t. Okay. So this language model is going to generate the next token. So the next token is basically the action that I'm taking. What token I should generate. So my output, which is pi of S, the output of the policy at that particular state, is the action that I'm taking at that particular time, which is the next token. And as we know, the output of the language model is basically the softmax. It produces a probability distribution on the set of actions, here the set of tokens that you can potentially generate, and you can use different sampling schemes in order to take your action. Therefore, here the set of actions will be basically the vocabulary that you have. Roughly speaking, you have 50K, if the size of your vocabulary is 50K, you have these number of actions, meaning that these are the number of tokens that you can potentially ask your model to generate. Okay, so you generate a token here, that's your action, and that takes you to what? To next state, which basically you add this particular token to the previous state, and that is your new state. As you can see here, there is no stochasticity in the environment. You generate an action. You take an action, you generate a token, and that's it. You add that to the state, and you deterministically go to another state. There's like no randomness, because the way that the language model is being, characterized here. So you don't have randomness at that point. Okay, and what is reward here? Reward is the quality of the response. That each time you get a reward, saying that, okay, up until now, how you're doing. It's good, bad, maybe, at the very beginning, maybe you're generating gibberish, so your reward is like really bad. Right? If you're generating high quality responses, then your reward is going to be good. And again, we are assuming we have a reward function. How do we have a reward function for language models? We did train a model, right? It's step 2. So we abstract that up. We are assuming I'm given a good reward model. Okay, so that's basically the assumption. All right, so 2 other concepts that I need to introduce before telling you how we can use reward model in order to improve the language model. So one concept is called value function. So what is a value function? First, I'm going to explain it in an intuitive fashion, so you don't need to remember any formula. Let's say you are at a particular state. Value function is going to assign some value to that state. Okay. So you're at you start with a particular state, saying that, okay, this is my initial state, and I'm going to follow a policy. That's it. So at this state, the policy is going to tell you to take a particular action, and it is going to take you to another state. Again, you're using the same policy. You use that policy to see what action you should take that will take you to another state, so on and so forth. And along the way, you collect some rewards. So at state 0, you have reward 0, reward 1, reward 2, up until the end. So if you're at state, let's say T, you have the final token, final action that you generated, you collect reward. And the value, according to the policy, starting at state S0 is just basically sum of these rewards. R0 plus R1 to RT. That's the definition of the value function. That means you start with a particular state and just follow the policy. That's basically quality of the policy, right? If this value is high, it means along the way, when you're starting with S0 and you follow policy pi, along the way, you're collecting a lot of rewards. That's good. The sum of the rewards are high. That's basically what it means to have a high value function at a particular state. So here, I assume my generation ends after T step. And usually in language models, that is the case. So you don't generate infinitely many tokens, right? But in general RL, sometimes you can assume your T goes to infinity. These are called infinite horizon RL problems, not in the scope of today's lecture, because today's lecture is about using RL in language models. But in those cases, I want to mention you can't add infinitely many numbers, because you're going to get like infinity. So in those cases, we use a discounted version of these summations. So for every future reward, you add a discount factor. You're saying that, okay, basically, if I give you $10 today, compared to like $10 tomorrow, probably you will take $10 today, right? So the tomorrow's $10 probably means a little bit less, maybe $9. So that's your discount factor. That's the gamma, and $10 2 days from now, probably worth a little bit, less. That's basically the way that we combine the rewards in order to have the reward and also have a well-defined function. So here's the definition for the value function. So another key element that I need is something called Q function, which assigns again a number to a state, like a value function according to a policy, but also an action. So the input to the Q not only is the state, but also an action. And the way that is defined is quite simple. It says, okay, so at the state S, I'm going to tell you the first action. But don't listen to your policy. So you take the action that I am giving you as your input, and after that, you can follow the policy. So you go to another state after this, let's say S2, and then after that, you follow policy pi and you collect rewards along the way. Collect rewards. That's the definition of the Q function. Yeah. Okay, so these are all we need in terms of the tools to understand deep reinforcement learning. The value function, the reward function, policy, and basically the definition of the states, actions, rewards, and the transition probabilities. So next, I'm going to show you a practical way to formulate a deep RL problem and optimize your policy in order to maximize your reward. But I'll pause here, see if there are any questions before I move forward. I think you had a question, or someone had a question? Yep.
For the policy, does that also not accept time as an input?
So policy, it depends on, you can have ergodic ones, you can have non-ergodic ones. Sometimes you can say at a given state that might characterize time itself. For example, in the language model, like, so you kind of get the information of the time because you know the length of the tokens that you generate. So what output you should generate. Sometimes that is not dependent on time. Right? It doesn't matter, let's say, for a robot, if it visits a particular state at time 0 or time t, if it is a fatal state, what action it should take. Right? So you can have like different characterizations of your policy. Very good question. You can, for the language model, we assume, time, which is basically the number of tokens generated, is characterized as the input to the policy. Yes.
I have a question about before the step. So where we were generating case samples and then picking randomly from that. So it seems like if you pick case samples and then sort of do some reward analysis on that, you're also intensively preferring that your output software probably should have a bigger variance, right? Because if it has smaller variance and there won't be as many options, so less likely to generate get a good human feedback. Is there anything meaningful to say about that?
So absolutely, right? So it really depends. These are like extreme points, right? Sometimes your next token, it is pretty unique, meaning that you have a very sharp distribution in your probability. Your entropy is low, right? Compare, or you call it variance. Maybe entropy is a better terminology here. Sometimes you have more options, and you can try to explore different options. I'm sure you can think about like, smarter ways of sampling to have a good trade-off between the quality versus the exploration that you have. But these are like the two extremes, and you can explore various versions. And I'm sure there are like zillions of different sampling versions people have explored. But good question. Yes.
I think I just missed it. Is the Q function and the value function two types of reward functions, or
No, the reward function is given or trained or learned, but we're assuming it is given. Value function tells you that for a particular policy, value function is defined with respect to a policy, saying that if you are starting with a particular state and you follow a particular policy, what would be the collected reward? So that's basically the sum of the reward or sum of the discounted reward. Q function, let me finish. Q function tells you, what if you start with a particular state, the first action I tell you, but after that follow that policy. So the first action you can violate the policy, the recommendation of the policy. What is the collected reward? And as you can see, I'm not talking about like the some of the foundations of RL. Obviously, that's not the focus here, but there are some equations, for example, Bellman's equations, that connects these two for optimal policy. Meaning that if you have an optimal policy that maximizes your reward, then if you look at the first action, that is the same as the action that your optimal, for the Q function, that is the same action that your optimal policy recommends, meaning that you cannot improve the value of the Q, even though if you have flexibility in choosing the first action. And that's how several, I would say, more traditional ways of training RL agents in terms of value updates, in terms of like the Q learning, so on and so forth, they have been formulated. But for time being, I'm just like not talking about any of those aspects, and I'm going to directly talk about something that people use in training language models. Yes.
Is there a reward model? Does the reward model bound its reward value like normally in RL applications, or are we not as concerned since it's a finite?
Fantastic. So there's a lot of research has been done on what to do with the reward model, right, in RL. Actually, that is one of the bottlenecks of training good RL agents. Because in many cases, you have some natural rewards, but those rewards are pretty sparse. So you, let's say if you want your robot to do some task, at the end, if it is accomplishing that task, that's fantastic. It's a high reward, but how to assign those rewards in the intermediate steps, it is a little bit unclear, right? And if you have a sparse reward, sometimes it is harder to train the policy. It's one of the difficulties that we have. But usually you want your reward to be well-bounded, most of the times positive, and you have like negative values if you're going into the state that is not desirable. Fatal states, you usually assign like a very high negative reward just to ensure that you are not going into those states. In the context of language models, for example, if you're generating some keywords or something that is, something that you absolutely want to avoid, right? So you can have like a very high but negative reward for those states, just to make sure that you don't step on those states even randomly. Make sense? Okay, one last question. Yes.
How do you decide the first action that you want to do?
Okay, so that's the input to the queue. You can pick any action. That's the beauty of it, and you'll see how that comes into the play. That's an input argument. All right, so let me carry on. Okay, so consider, okay, as I mentioned in response to one of the questions, there are many different ways of finding a good policy, but I'm going to talk about some approaches that is used in training language models. And we are going to characterize a policy itself as a neural network. So policy, as I mentioned, is a function mapping your states to actions. So I'm going to parameterize it using theta, and I'm going to characterize it as a neural network. That's my policy parameterized by theta. Whenever it has an state, it will produce an action or a probability distribution on the set of actions I have, and I can randomly select one of the actions according to that probability. So that's the policy in it. And it is not surprising to you because I already motivated the whole thing using a language model, and this is precisely how a language model works. Therefore, the parameter theta determines your policy, and the parameter theta in the context of language model determines your language model. Your language model is a policy. So we use these interchangeably. Okay. Let's see how we can optimize. Now, my goal is to find a good theta. What does it mean to find a good theta? A theta that maximizes my collected rewards. And we are going to formulate it. Suppose you start with at state S1, you follow your policy, basically take an action A1, you go to state S2, and you repeat it T times. You take an action. These are, for example, the tokens that you are generating along the way. And at each step, you are collecting a reward. So this is called, let's say, RS1A1. The reward for the next action or token, the reward for the final action or token. And for simplicity, I'm going to, instead of every time just saying that, okay, you take an action, you generate another, you go to another state, so on and so forth, I'm going to call this a trajectory. And I'm going to show it with tau. Trajectory. Basically, along the trajectory, you go to different states by taking different actions in your trajectory. Okay. So first of all, let's see what is the reward associated to this particular trajectory. Because at the end of the day, we want to pick a policy that gives us like the highest reward. So the reward is just the sum of the rewards that we collect along the way. That's as simple as that. So I'm going to look at my first reward, my second reward, up until the last one. Simple. We want to maximize the reward function. Okay. So the second thing we need to know is that if I give you a trajectory, how likely it is to see that trajectory using your policy? What is the probability of observing that trajectory according to your policy? Again, in the context of language model, if I give you a response, what is the probability that you would have generated that response using your language model? Right? I'll show that as P sub theta of tau. What is the probability of observing this particular sequence of text or trajectory, or however you want to call it, according to a language model, according to your policy, parameterized by theta? And if you notice, I'm going back and forth just to really engrave the connections between RL and language models, hopefully in your brains. Okay. okay, so what is this probability? Obviously, we start with the probability of the first token, or maybe you always start with, some start token, not really important. And then you see where your language model takes you. With some probability at step T, your language model takes an action A sub T, meaning that generating a particular token. And for the language model, if you do that, you deterministically go to another state. But in general, you may have some stochasticity in the board. This part is not very important. Because for the language model, if you are at state ST, you take an action AT, you always go deterministically to the next state because you just add that particular token to the end of your sequence. But in general, there is a transition matrix after you take an action that can probabilistically take you to another state. That's basically the probability of observing this particular trajectory according to a particular policy. Okay, so what is the goal here? My goal is to what? Is to maximize my reward. Find the theta that maximizes my average reward. Let's say I generate a trajectory with some probability, and I'm going to take the expectation over that probability. So this is going to be my average reward. That's basically the quality of your language model, right? So if you have a good reward function. And we want to maximize this. So usually we call this J theta. It's a function of theta. All right, so I have an optimization problem. I want to find the theta that maximizes this particular objective. So what should I do? What would you do to find a good theta? Maximum might do it, but you have already an optimization, right? So max over theta of j theta. So what is the algorithm that we know how to use in order to solve such maximization problems? Gradient descent or gradient ascent in this case. Right? Just take a gradient step to maximize your theta. This is called policy gradient because theta determines your policy and you are using gradient in order to maximize this. It's as simple as that. Policy gradient. So as you can see, policy gradient is nothing really fancy, right? So what we did is we characterize our policy using a neural network. For a sequence, we want to see what is the probability of that sequence generated by that policy, and what is the reward associated to that. So therefore, we can look at like the average reward for that particular policy, and I want to pick a theta that maximizes this reward function. I can take a gradient. That's called policy gradient. So one difficulty here is that how to characterize the gradient, because here, as you can see, the expectation over p sub theta of your trajectory, tau. So how to compute the gradient? And that is where you get to see a lot of different algorithms implementing policy gradients. Different approaches in order to approximate that gradient and use in a gradient ascent fashion in order to maximize the expected collected reward for that particular policy. So next time I'm going to talk about the most popular approaches to tackle the policy gradient and how we use it in order to improve the language model. Thank you. Okay, so we ended up with this optimization problem, maximization over theta, the expected reward, and we want to use policy gradient in order to optimize this. In order to use policy gradient, we need to compute the gradient of the objective. Okay, so let's look at this gradient of the average reward. So my trajectory is according to this distribution, P sub theta. Theta is the parameter I have for my policy network, and I'm looking at the average reward. So one question, can I put this gradient inside the expectation? Yes or no? So expectation is a linear operator if it doesn't depend on the parameters that you're optimizing. So in this case, you cannot take the gradient into the expectation. If you remember the BAE lecture, when we were optimizing the decoder side, we had a similar problem, that you couldn't take the gradient into the expectation, and there we used a reparameterization technique in order to have the expectation somehow disentangled from the parameters that we have, and after that we can take the gradient into the expectation. Okay. So again, we can't do this simple gradient calculation. So let's take a closer look at this expectation. I'm going to think about a continuous case, so I can write this expectation as the integral of the reward for a trajectory tau times the probability of that trajectory times d tau. So that's basically the expectation part. Now I can write this as the gradient of the density times d tau. Okay, but the problem is how to compute the gradient of the probability of a trajectory according to parameters tau. Right? This term is not easy to compute. Again, remember, P sub tau of tau is according to this formula. So there it comes, a really nice property slash a trick that is used in policy gradient. Let's call it a nice trick or property. Okay. If I look at the probability of tau, trajectory tau times the gradient of log of this probability, let's see what I get. What is the gradient of log function? Let's say log of u. What is the derivative of log of u with respect to u? And the derivative of u, right? So derivative of u divided by u. So let's do that. So then this is equal to P sub theta of tau times the derivative of the argument, which is P sub theta of tau divided by P theta of tau, right? And as you can see, these two terms cancel out. And then you get this as gradient of P sub theta of tau. Just a mathematical reformulation that we have here. And look at the right-hand side. Isn't the right-hand side exactly the term that we have inside the integration that we have? So I can, instead of looking at this, I can look at look at this left-hand side, they are equivalent. But you may say, okay, wait, the left-hand side is more complicated. It looks more complicated than the right-hand side. So what are you doing here? So let's take a look. So let's call this equation 1. Let's call this equation 2. So 1 plus 2, we have the following. The gradient of our objective is equal to the reward for that trajectory times the gradient of p sub theta, but not instead of that, I'm going to write the gradient of log of p sub theta of tau times p sub theta of tau times theta. So I replace 2 in 1. Okay, but can I simplify this equation a little bit more? So you have a function of theta, and that is multiplied by this density, and it is averaged over this density. What is it?
Expectation.
It's an expectation, exactly. So I can write this as the expectation over the density that I have of this argument, which is the gradient of log p sub theta of tau times the reward. This is the foundational equation for policy gradient. Because I wanted to compute the gradient of my objective, but I didn't know how to do it because the expectation was creating issues for me. So I couldn't take the gradient into the expectation. With this technique or property or trick, I can write the gradient as another expectation, which means that I can potentially generate n samples, n trajectories, and approximate this expectation by 1 over n sum of 1 to n of this value over these trajectories that I generate empirically. Trajectory I times the reward. Now I have a practical way. If I could compute the inner argument, which I will argue that can be easily done, I can compute the gradient or an approximate gradient of my objective function. I can follow that gradient. I can optimize using gradient ascent. Okay. So 2 questions here are left. What is the first term? What is the second? So how can we think about these 2 terms? So let's first think about the first term. Okay. Just as a reminder, what is the probability of a trajectory? We had that previously, the probability of the first state that you start times 1 to t. You follow your policy according to parameters theta, the probability that you take action at at state st, and then what is the transition that you have to the next state. That's basically the same formula we have. Right, so if I look at the gradient of this according to theta, first let's look at the log. Let's apply log, because I'm going to take the gradient of the log function. So if I apply the log, So I get the initial probability that I start at a state. Maybe I will always start with, the start token or whatever token that you're starting. And then this product will turn into summation because I'm applying a log. This will be log of the first term plus log of the second term. Now let's see what happens, because at the end of the day, I'm interested in the gradient of the log function. What happens if I take the gradient with respect to theta? This doesn't depend on theta. This also doesn't depend on theta. It is a transition matrix. And the only term that depends on theta is this one. So therefore, I can just simply write this as gradient of log p sub theta at given st. And that's it. Right? So that's basically the first term in my gradient equation. So what about the second term? What is the reward for a trajectory? It is simple, right? So it is just the sum of the rewards that you have collected along that trajectory. I can write this as the following. So this is just the sum of rewards that you have collected along the way for trajectory I from T1 to T. So here's our gradient formulation. I have now a good characterization for the first term. I have a good characterization for the second term. Let's put these things together just to have all of it in one picture. Again, I have an objective, j theta. I want to compute its gradient to optimize. The gradient of my objective, therefore, can be written as sum over 1 to n over n trajectories. For each trajectory, I have this term, log of p sub pi of theta times the reward. Again, this is exactly this equation. So the only difference here is that the first term, I replaced it with the equivalent characterization, and the second term, I replaced it with the equivalent characterization. Okay, so let's get a little bit of a feeling about this equation. Okay, first of all, j theta, what is it? It is a scalar, right? It basically gives you the average reward associated with a particular policy. You want to maximize it. And theta is the set of parameters that you have in your policy network. Gradient of j theta, is it a scalar or is it a vector? It's a vector of size, model size, the same number of parameters that you have. If you have 7 billion parameters, this gradient will be 7 billion, a vector of 7 billion size. Maybe you are not going to like update all of your parameters, but that's for another discussion. Okay. So this term, it is basically the sum of rewards. It is scalar. It's a real number. But what about this term? So pi theta is the output of your neural network. For a given state, it tells you what is the probability of that particular action. You take the log, and then you look at the gradient of your neural network with respect to theta. Then this will be a vector the same size as basically the number of parameters that you have. So this is a big vector. And you take the average of this vector along your trajectory. So for every time you have a vector, you look at the average. So that's basically your average gradient. And then you take another average over the batch size that you have, the number of trajectories that you have generated. So this is very much computable for you. For a particular theta, you can generate n trajectories. Then you can run backprop on your policy, compute these vectors for each trajectory at different time, take the average and multiply it by this scalar, which is the sum of the reward. And then you have a vector, you follow that vector, you optimize. It is computable, you can absolutely use it. But in practice, there are some changes to this optimization, to both objective and similarly to the gradient. And one issue is, that people, they have done maybe some heuristic changes, is to control the variance, because here you're generating some trajectories, but the space is huge, right? So based on like the scale of your rewards, you may have like a huge variance that may require generating like thousands of tens of thousands of trajectories for each gradient computation, and that is not very stable, very difficult to have it converge to a good solution in practice. Okay. So there are some practical changes to make it more practical. Okay. So what are those changes? For now, I'm going to drop this batch just to simplify notation. We are assuming batch size of 1, but you can take the average just to just focus on the inner arguments. Okay. So the first argument is going to be very similar to what we have computed. It is going to be the gradient of your log probabilities, basically the output of your policy. But for the second term, instead of multiplying with the sum of the rewards over that trajectory, we are going to multiply it with another number. This is called advantage function. And it is defined as the following. Okay. So if you have a policy that is taking a really good action, let's say you have a sequence of words, the next word is like amazing for that you're generating. So you want to encourage that direction for your policy. On the other hand, if the action that you're generating or you're taking is not good, then you want to penalize it. You don't want to go into the direction of that particular action. So that's basically the way that advantage function is formulated. So you look at the queue at state S theta, so you're at the state ST, when taking action AT, the action that you are looking at the moment, and you subtract it with the value at that particular state. Basically, it tells you you're at the state ST and you're taking this very particular action. What is the quality of this action? So if you take this action and then follow like maybe the older version of the policy that you have, versus you don't make any changes and you follow the older version of the policy that you have. So if this action is better than your older policy, this number is going to be positive. On the contrary, if this action is not as good as even like the previous version that you have, this number is going to be negative. So that's basically the intuition behind the advantage function. There are many different ways to estimate a good advantage function that doesn't have like a huge variance. I'm not going to go into the details, but roughly speaking, again, I'm adding like a hand wavy here. Roughly speaking, the way it works, you run your older policy for a few steps and have an estimate for the value and for the Q, and use that as your advantage function. This is usually called temporal difference learning. But there are many other strategies to estimate a good advantage function. Okay, fantastic. So up until here, everything was rigorous. Then we did a little bit hand wavy stuff. We kept the first term. Instead of like the sum of the rewards, we are replacing it with an advantage function. Meaning that what is the advantage of taking a particular action at a particular state? If it is advantageous compared to the previous version, we encourage it with a positive advantage. Otherwise, we try to discourage it. So this is the gradient, obviously, of a new loss or new objective, right? Because we changed the original objective, then we change the gradient, then the original objective also has been changed. So what is the objective whose gradient is this one? Because usually in deep learning frameworks, you have a loss and then you can call your gradient optimizer in order to compute the gradient. So the loss corresponding to this particular gradient is as follows. It's obviously a function of theta. We call it a loss of policy gradient. It is expectation over your trajectories, log of the first term times the advantage. And if you think about this, if you take the gradient of this loss function, so the gradient of the first term is gradient times advantage, and since the advantage doesn't depend on theta, the current theta, the gradient is zero, therefore the other term becomes zero. So this is the loss that you can think about. That's it. This is called policy gradient. Okay, so when it was introduced, it worked pretty well on some scenarios, but still it had some instability issues. it was better than the original version, but still it was suffering from some instability issues. And the main reason behind such instability was the fact that your outputs can change quite a lot from one update to another update. So you may not have like a smooth way of transitioning along the optimization path that you have over the set of parameters. In order to remove some of those instability issues, two algorithms on top of this have been proposed. One algorithm is called trust region policy gradient, trust region policy optimization in 2015. They basically use the same objective function with a small difference. So they maximize over theta, expectation over the trajectories. Again, you have an advantage function. Instead of looking at the log of the policy output of an action given a state, they look at the ratio of the policy with respect to the older policy. They look at the basically probability of this particular action according to this policy at this state using theta compared to the previous one, which can be assumed a fixed set of parameters in the optimization. So this is called a ratio. Ratio of change. And they want to make sure that the new policy and the old policy, they are not very different. So they add this KL distance between the old policy. It's a probability distribution over actions. In the language model, it's basically the vocabulary and the policy according to data. And you take the average over T. And you want this to be small. Basically what it does is it says, okay, look, you want when you're updating your policy, meaning in our case, your language model, you don't want to change your language model a lot. So it's from one update to another update. If for a particular set of inputs, set of tokens, your language model has a high probability of generating a particular word, it should also have a relatively high probability to generate the same word, but maybe with some small changes. That is the definition of KL, to have a bounded KL. So you are not saying that, okay, my language model thinks the next word should be, let's say, apple for this particular sequence. I update it, and now it thinks the next word should be like Donald Trump. Right? So those are the behaviors that we want to avoid, to have basically a huge change in the output of the model to make it smooth. The rest is the same. So the only difference here is that they don't use the log and they use this ratio. And I couldn't find a good theoretical justification, but I imagine that came from some of their empirical experimentation. Okay, so that's the trust region policy optimization. Just we have one more step, and believe me, we'll be done with deep RL. So the next algorithm is extending or modifying this trust region policy optimization, even though this worked much better than the original policy optimization in terms of stability, it had one really big issue. And that issue was this constraint, this KL constraint. It is nice, but also hard to implement. It is not as easy as other unconstrained versions of objectives that we are used to in deep learning. Okay. So that takes me to the next algorithm. It is called proximal policy gradient. In 2017, this was developed by a team at OpenAI. And their idea was quite straightforward. It was the same objective as before, max over theta, looking at the expectation over the trajectories. Again, they look at the optimization of the ratio times the advantage. It's the ratio times the advantage. But to ensure that your policy don't change too much, they just clip. They clip the change in your ratio. So if the ratio changes more than epsilon, they clip it to, basically they have an upper bound and lower bound. This ratio is if the output of the policy before and after is the same, then your ratio is 1. And if you encourage it a little bit more to generate this token compared to the previous version, the ratio will be like 1.05. If you discourage it a little bit, the ratio will be like 0.95. But you don't want to like jump to like out of a sudden from like 1 to like 10,000. That's precisely what they do. Instead of the KL, they just clip this ratio between the two numbers, 1 minus epsilon and 1 plus epsilon. And this clipped version is also multiplied by the advantage function. And they look at the minimum of these to be conservative. Basically saying that if you need to change your output from this ratio from 1 to 1,000 to maximize your objective, don't do it. We are not going to accept that. So we want to be conservative in updating, even though you think that, oh, like you may find the direction and then you are going to like go as far as you can. And I believe in their implementation, they use epsilon 0.2. So the nice thing about this is it is unconstrained. It is much easier to implement, and it is more stable. So this is called PPO algorithm, proximal policy optimization, PPO. So when they talk about, oh, we are using PPO, that's basically it. So now hopefully you know the background story, how we ended up, because if someone shows you this equation about like PPO, it may not be very intuitive, but with this background story, hopefully you saw different steps and different changes according to the previous step taken for the optimization. Okay, so that is it in terms of a very quick recap of deep reinforcement learning. As I mentioned, deep reinforcement learning is a course itself. You know, I'm just skipping so many details, but we focused on the most relevant part for training the language model. Okay, so I'll pause here, and next we'll revisit the steps of training a large language model using human feedback in the loop with the knowledge that we currently have with respect to deep reinforcement learning. Yes?
Just a clarification question. So when we clip the gradients, does it still preserve the direction of the update? So when we do the gradient here, RT of theta is a function of theta, so it will give a vector with the direction, but 1 minus epsilon plus epsilon is just a scalar.
Yeah, so it clips it bounds the ratio, not necessarily, it is not necessarily bounding the step size, for example, that you are taking, if that's your question. It bounds the ratio. Again, it is a simpler version of the KL divergence that you can think about. Other questions? Okay, so practically speaking, what do we have? What have we learned? Oh, right, so you give me a reward function. I'm going to have a policy network. Right? So you give me reward function, or I am going to, okay, so also you tell me what network you want to use for your policy. You pick a neural network. It maps your states to actions. That is your policy network parameterized by theta. And that is it. I can use one of the algorithms I mentioned, including proximal policy optimization, to find or update my theta. That is it. And the whole discussion that I was having is to tell you what this PPO is. But now, hopefully that you saw what PPO is, now you can think about it as an optimizer. What is the input to this optimizer? Your reward. I'm not optimizing the reward. The reward is given. The policy network, the network architecture, maybe some initialization. And using that reward, we can update this policy. So that's basically a high-level summary to view PPO as an optimizer. Now let's go back and revisit the 3 steps of training a language model. Training a large language model. And sometimes people, they refer to it as reinforcement learning with human feedback. RLHF. It's a fancy name. In my opinion, it's more like a branding than what else. Okay, so step 1 was very straightforward. Supervised fine-tuning. We take a GPT model, GPT-3, GPT-4, have a lot of demonstration data, do a supervised fine-tuning, very expensive, supervised fine-tuning. So step 2, we learn a reward model. It's called reward model. That basically tells me what is the quality of a response with respect to a particular prompt. So that's basically the reward model that I have. Reward model. You have a prompt. you have a response, and you want to have a scalar. And the way that we mentioned, in terms of training of this reward model, you ask human annotators to rank different outputs of a language model, or different versions of a language model that you have, and use some approaches to turn those ranking to numbers. There are like approaches like ELO, other approaches that I won't go into it, but you can look at some of those technical details. Here is the place that you can quote unquote align language model with human preference. So if you are hearing about alignment, this is one approach to think about this, saying that if your language model is generating, I don't know, some style or something that you don't want your model to generate, maybe you can integrate a reward model to penalize those types of generations. Some toxic content, some biased content, so on and so forth. Okay, so just to give you an idea, for the, I believe the ChatGPT based on the GPT 3.5 for the OpenAI, the language model, GPT-3 in fact, is it has 175 billion parameters, but the reward model that apparently they use is much smaller, 6 billion. But that may not be necessarily the case in all other models. For example, in the one that Anthropic company is training, both language model and reward model has, roughly speaking, similar number of parameters, 50, close to 50 billion. And there are different design choices that you can make here. Obviously, these are very active areas of empirical research. Okay, but anyway, so let's assume we have a reward model, and step 3 is where we are going to use or fine-tune the base language model using the reward model. So first of all, in this step, not all parameters are usually changed, because your original model may have, I don't know, like 135 billion parameters. You are not using reward to change everything. So usually a small subset of these parameters are updated in this particular step. So not all parameters are changed. And we are going to talk about different approaches for fine-tuning that is parameter efficient after this topic. Okay. We are going to use a deep RL optimizer like PPO or something similar to update language model. Again, PPO needs a reward. You start with whatever your language model has pre-trained. So you start with that. Look at the subset of weights that you want to fine-tune and use your PPO optimizer. Hopefully now you know what is going on behind the scene in order to update those parameters. So you start with a base model, and I can comfortably write the base language model using Pi, because we know the language model can be viewed as a policy. So hopefully you are comfortable with this terminology. So it has an input prompt, X, an output response, let's call it Y. So we want to make it better, do a little bit of fine tuning, quote unquote, with reinforcement learning with human feedback, meaning that we want to have X with a Y that is better compared to perhaps the base model that we have. And in order to do that, we are going to use a reward model that we trained in the second step. Let's look at that. Okay, so this model takes two inputs, X and Y, prompt and respond, and outputs a reward value, which is a scalar. Okay, so here you have two options. If you feel good about your reward model, then you can just use policy, proximal policy optimization, PPO, just to update a subset of weights in your base model to get a fine-tuned, hopefully a better model, more aligned model. Okay. I'm sure people have done it, but what it does is that even though your reward and you're using PPO, it's bounding the ratio of change, etc., etc. But since these models are huge, like order of billions of parameters, you can overfit to your reward, meaning that you can generate some outputs that, even though with all of these thresholds that you have, it is losing the quality of generation from the base, and you just try to maximize the reward. So in order to avoid overfitting, to avoid overfitting to the reward model, in practice, people use the following reward instead of the original reward. So what we use is the original reward, but your good friend KL comes back from dead, and you penalize the KL of the output of your model after the PPO optimization, after the fine-tuning, with respect to the base model, which you can think about as the constraint that you have in the trust region policy optimization, right? So that's a regularization that usually it is being added. Lambda is a hyperparameter. Again, if you're updating your model too much, then your reward is going to be bad. And that's another way to ensure that you are not overfitting to the reward model. And you use this reward in the PPO to update subset of the parameters that you have using the policy gradient optimization. And that is it. That's how you get a quote-unquote aligned large language model to human preference, or you can call it training large language model with human feedback in the loop. Obviously, this is maybe active is underselling it. It is a super active area of research. And who knows, next time I teach this course, I may not cover any of these. But this is how many of the state-of-the-art language models, to my knowledge, have been trained, or they are trained. And as you see, there aren't a lot of revolutionary changes compared to the previous versions. The models have become significantly bigger. Let's say from the previous versions with less than 1 billion parameters. Now you can easily talk about models with plus 100 billion parameters. In fact, there are some mixture models that can be even much bigger, order of 300 billion or more parameters. The number of samples used in the training of these models have also been increased a lot. And people have observed the quality of the training data plays a huge role in training high quality models. So bigger models, bigger / higher quality data. The first two steps are human annotations, human data, human label data. And that plays an important role in order to have a good starting point for these language models, to have different inputs and outputs used in supervised way for fine-tuning these models. And perhaps like the one, in my opinion, more interesting technical way of training these models is done via policy, proximal policy optimization, where again, the idea, if you think about, the core idea is that you are still getting some human feedback to characterize a reward model, and you just use that signal. Since you asked earlier in the lecture, you use that signal to adjust your output probabilities, and that is it. So you can forget about all of these fancy terminologies. You want to use that signal in order to say, okay, so I want to increase my probability a little bit, but not too much. That's the KL thing. And that is it. That is the heart of maybe the hype of large language models.